boundary conditions around some surface charge distribution. Let's say you have a surface charge distribution with surface charge density sigma. We'd like to know the difference between the electric fields uh, above and below the surface charge density in the perpendicular as well as the parallel directions. So there are two cases. One is for the perpendicular direction and the other is for the parallel direction. Perpendicular to the charge distribution and this is parallel to the charge distribution. In the perpendicular case, what we did is we took a box, a pill box, whose height is very negligible. It means this rectangular box is very close to the charge distribution. So it has a surface on the top and surface on the bottom, each of which is represented by an area vector a1 bar and a2 bar whose magnitudes are the same, which is a. Uh, the sides the side faces of this box are negligible. They're too small because the height is small, so we're not going to consider anything from there. And a1 bar and e bar perpendicular. E bar above perpendicular component is both of them are in the same direction, and these two are in the opposite directions. So when I'm trying to find E bar dot dA bar, if you use Gauss law, we know that it is equal to Q enclosed by epsilon naught, and Q enclosed is nothing but area into this charge density sigma, so sigma A by epsilon naught. If I open this, I'm only considering the dot product between this one and A1 bar and this one and A2 bar because the other faces are too small, so there won't be any contribution from it. And there is no perpendicular component. Like if you have any perpendicular component, that will be perpendicular to the side faces. So dot product will be 0. So either ways, nothing is going to come from there. So only two parts are here. Since these two are in the same direction, there is a plus here. These two are in the opposite direction, you have minus here. And A1 and A2, their magnitudes are A. So they will get cancelled. A gone, A is gone, A is gone from here as well. So this is what remains. So the electric field is discontinuous uh, above and below charge distribution, a surface charge distribution. That is the result here. In the second case, instead of taking a box, I take a loop where L1 bar represents this vector, the above line, and L2 bar represents this vector, right to left. And since I've mentioned here that this side lines, whatever they are, they're they have very small length. They have negligible length. So when I take E dot dl, these side loops will not contribute to anything. And even if you look at it this way, the electric uh, field component along the parallel direction, if you take a dot product between that one and the loop which is on the sides, the angle between them is 90 degrees. So again, dot product is going to be 0. So there is no contribution from these two sides of the loop. The only contribution will come from the top portion and the bottom portion. These two are in the same direction and these two are in the opposite directions. Okay, even the magnitude is same. The loop is a rectangle. So if I try to evaluate E dot dl using Stokes theorem, I can write this, and we know that the curl of electric field is 0. That's a known result. So this is 0. E dot dl will be this one. You have only two parts, E parallel above and E parallel below. These two are in the same direction, so there'll be a plus. These two are in the opposite direction, so we'll get a minus. L is a constant. I can bring it out and send it to the RHS. L is gone from this equation, so these two are results. So this means that the parallel components of electric fields are continuous. Perpendicular components are discontinuous. We can extend the same discussion to potentials, potential above and below. So at this point, there is potential V above. At this point, there is potential V below. there is some blue line joining these 2 points, and I'm telling the length of that path, this line is negligible. So that means I'm finding V above, just above this, just above this surface charge distribution. I'm trying to find V below, just below this surface charge distribution, just above and just below. That's why this is of negligible length. And here n cap is just the direction perpendicular to this surface charge distribution. Basically, we can say basically this direction, the direction of this blue line is n cap. Anyways, so the same story, V above minus V below, I can write it like this: gradient theorem. This is the gradient theorem, and I know that gradient of V is nothing but minus E bar, fine. And I told that its length is negligible. So if I try to find the line integral along this, it's going to become zero because length is very small. So I can declare that this is zero. So V above minus V below will be zero. So V above will be equal to V below. So the potential is continuous. There is no discontinuity. That is the result of this one. In the bottom, I did something. You can see it's very simple. I know this. I know this. For above, I'm doing applying the same thing. For below, I'm applying the same thing. E is equal to E perpendicular plus E parallel. That is fine, and we know this result. If I subtract one equation from the other, you'll get this big one. So it's just that the gradient of V above minus gradient of V below is nothing but minus of sigma by epsilon naught n cap. How did I get this? Because we know that E above minus E below is sigma by epsilon naught. That is how I got this equation. I wrote n cap because the direction is important. This is gradient. Gradient of a scalar field is a vector field. So there is a vector field on the LHS. There should be a vector field on the RHS as well. How n cap, direction of E perpendicular above minus E perpendicular below is, it is upwards. So that is why I wrote n cap, where n cap is the direction above the surface charge distribution. So two results for the boundary condition. One is for the electric fields and the other is for potentials. Yes, there is nothing much to boundary conditions. Here is a formula digest. We, I mean, all of this is very much known. There is nothing much to be told here. We looked at this previously. This is the Poisson, or you call it Poisson, right? Poisson equation. Potential difference. Curl of electric field is zero. This is Gauss's law, but in differential form. We know this. All of this is known. Yes, that's it. There is nothing much to be told here, and this shall end here. Yes, thank you.